Look across any rural highway, and you'll see them. Hundreds of miles of transmission lines, suspended high above the ground on wooden and steel towers. Step into a major city, and those towers vanish. The heavy flow of electricity is still there. It's just been routed deep beneath the pavement. A common assumption attributes this to city planning, the idea that overhead lines are simply the cheaper, uglier option, while cities bury their cables strictly to save space and clear up the view. Cost and space certainly play a role, but the physical laws of electricity dictate these design choices. The way our power grid is divided between the sky and the dirt is a matter of physics. Moving high voltage through the open air requires an entirely different set of electrical properties than pushing that same power through conductive earth. When engineers build overhead lines, they take advantage of a distinct engineering advantage: open air. Air is an excellent natural insulator, and it happens to be completely free. Because of that, the heavy, bundled conductors carrying the power are entirely bare. They do not need a thick rubber coating. They need to be suspended far enough away from the steel tower so the electricity doesn't arc across the gap. The only physical protection required is a string of glass or ceramic insulators. That small barrier is all it takes to keep the voltage from traveling down the tower structure and into the ground. Underground, that advantage disappears. Dirt and groundwater are highly conductive, meaning you cannot drop a bare wire into a trench. To keep the electricity from escaping, an underground cable has to manufacture its own isolation. This cross-section shows the required anatomy: a central copper core surrounded by thick cross-linked polyethylene insulation encased in semiconductor shields and finally wrapped in a metallic outer sheath. What takes a simple bare wire in the sky requires a highly engineered, multi-layered pipe when buried. But wrapping a high-voltage wire in tight layers of insulation and metal shielding introduces a severe invisible problem: capacitance. Capacitance is essentially the ability of a system to store an electrical charge. It happens anytime you have two conductive materials separated by an insulator. In an underground cable, the inner core and outer metallic shield act as those two conductors. Packed mere inches apart over miles of distance, the entire cable transforms into a continuous capacitor. As alternating current pulses through the line, it constantly charges and discharges this capacitor. This generates a parasitic charging current. The longer the underground cable gets, the more reactive power it absorbs, eventually choking off the actual useful electricity you are trying to deliver. Overhead lines avoid this trap. The vast spacing between the wires in the open air means their capacitance is incredibly low, leaving the full capacity of the wire available for useful power. If we tried to bury a standard alternating current line to cross a continent, the charging current would consume 100% of the power capacity before it ever reached the next state. These physical differences also dictate exactly how the two systems operate under stress and what happens when they break. Overhead lines are constantly exposed to the elements. They get struck by lightning, blown over by high winds, and tangled up in falling trees. However, up to 90% of these issues are temporary faults. If a lightning strike causes an arc, a circuit breaker trips to cut the power. In a fraction of a second, the surrounding air deionizes, the breaker automatically recloses, and the power flows again. Underground cables are largely immune to weather. But when they do fail, often from degraded insulation or an accidental backhoe dig-in, the damage is permanent. There is no automatic reset. Crews have to use specialized equipment to pinpoint the exact location of the hidden fault, excavate the street, and painstakingly splice those complex insulating layers back together. This creates a stark operational trade-off. Overhead lines fail frequently, but can clear themselves instantly. Underground lines fail rarely, but when they do, a quick flicker becomes a multi-day blackout. When you combine the need for heavy insulation, the physics of charging currents, and the extreme difficulty of maintenance, the math becomes unavoidable. Installing an underground cable routinely costs anywhere from 3 to 10 times more per mile than building an equivalent overhead transmission line. This is why overhead lines dominate rural areas and long-distance transmission. Open air is a free insulator, capacitance is near zero, and the physics of moving power over hundreds of miles remain efficient. Underground cables are strictly reserved for dense urban networks. In these environments, extreme space constraints and public safety justify paying the steep engineering premium required to bury the grid. The electrical grid that surrounds us is a strictly calculated compromise between the limits of human engineering and the absolute laws of physics.